cosmic gardening. I've been studying how we plant supermassive black holes in our galaxy models. So before coming here, I had never studied galaxies before or supermassive black holes. I mostly, with gravitational waves, studied stellar mass black holes. And there are still unanswered questions about how those black holes form, but at least we know they come from stars. There are black holes out there that are billions of times more massive than stellar mass black holes, and spatially they'd be bigger than entire solar systems, and we have no clue how they could have formed. Now we have new data that is pushing more backwards in time, as we've already heard during these talks, and most of us know. The James Webb Space Telescope is looking very early on in the universe, and as far back as we look for these black holes, we see them. So how did they form so early and get so big so quickly? So it's a very timely environment for studying this stuff because we have the data now that we can match to our theories, because there's a number of theories on how these could have formed. So the question that I'm interested in is which black holes will actually have signatures of their seeding? Which black holes or which galaxies can we look at and tell the differences between different formation models? So there are a number of tools people use for studying galaxies, and before I came here, I didn't know the difference between a semi-analytic model or a simulation. So this is a very simple explanation on the differences between these. Simulations solve full sets of equations that could be for gravity, thermodynamics, fluid dynamics. Sometimes people throw magnetism in there. And this describes how the different components in the galaxies evolve. So the gas, the dark matter, stars, and so on. But these are very computationally expensive because you're solving all of these different equations in full. It takes a long time to run these, and you can't fully explore your parameter space. On the other hand, you have semi-analytic models, where instead of solving the full detailed physics equations, you solve simplified expressions that describe the flow between different components. So for example, how much gas is being turned into stars? How much gas is being expelled from your galaxy? How much is falling back into your galaxy, and so on. And these are much less expensive and are more flexible to explore more parameters. And so with this project, my supervisor was Rachel Somerville, so of course I was using the Santa Cruz semi-analytic model. To give an idea of what has been done in seeding so far, before we adjusted the Santa Cruz semi-analytic model for my project, it would just put a seed in everything. Every single galaxy got a black hole, and it didn't matter any properties of that galaxy, just everything got a black hole. Other semi-analytic models have a bit more detail, so a recent work puts black holes in galaxies that have a sufficient halo mass, so they're massive enough, and they have enough gas in their galaxy, and they have low metallicity. Simulations, on the other hand, are sometimes more simple in the way that they add black holes to their galaxies. So a lot of the time, there's just a halo mass threshold, so if you have a heavy enough galaxy, like 1 times 10 to the 10 solar masses, you'll get a black hole, and if you're less massive than that, you don't get a black hole. And then there are some others, such as Romulus or Brahma, who are now considering the internal gas properties of galaxies and putting a black hole in places where there's dense gas or there's metal poor gas. And so what is unique about my project is I'm combining the internal gas property information that you get from a simulation with the computational flexibility of a semi-analytic model. So to give more context on this, like I said, I'm using the Santa Cruz semi-analytic model. And I'm using from the Brahma simulations information about the dense metal poor gas mass. So these are full cosmological hydrodynamic simulations that were designed specifically to study black hole seeding. And Claude Boehmich, who is the lead author on this and was one of my mentors this term, before I got here, they did a symbolic regression to get from the Brahma simulations a relationship between the dense metal poor gas mass in a galaxy and the star formation rate of that galaxy, and the average gas metallicity. So the Santa Cruz SAM gives you the star formation rate, and it gives you the average gas metallicity, but you don't know the internal details of what's going on in each galaxy. But now, with those values that you get from the model, we can estimate how much dense metal poor gas mass is in each galaxy. So, for example, in this model here, Evans et al. 2024, they used the global property, so you could underestimate the number of seeds you get because you only use galaxies that the average is low metallicity. But in our model, we could have a galaxy that has higher metallicity, but because of our expression that we get, we know that there could potentially be pockets of low metallicity gas in there. And so, I'll skip ahead. I did this in a different order than I practiced it in, but this makes more sense. This is from a Clant. It is the fraction of dense metal poor gas mass in a galaxy as a function of metallicity. And so the colored squares are from the simulation, and the black line is the symbolic regression that was fit to it, and it's what we put into the Santa Cruz Semi-Analytic model. And so it lies on top of it and looks like a pretty good fit, but you should be wondering, there's a lot of scatter there. Does that matter? And it doesn't seem like it matters. This is the number of seedable halos, which is what we care about. We want to know which halos are getting a black hole as a function of redshift. And the solid lines are from the simulations, the full detailed solving all the equation simulations. And the dashed line is from the symbolic regression. You can see that these are very, very close. To go back now, the backbone of the model that we're using are these graphed merger trees, which were specifically designed for high redshift. So it tells you how many galaxies are going to be in your model and how they interact with each other and so on. And so I'm using 3 different box sizes. These are of 5, 15, and 35 megaparsecs on a side. And the reason that I'm using these 3 different box sizes is that the different volumes have different mass resolutions. So this is showing the number of halos that have a specific mass. And you can see for the smallest volume box, graph 5, it has the highest mass resolution. So you can see the lower mass halos. And on the other side of things, graph 90 is the largest volume, and you get the larger mass halos. And I want to see how black holes form in all of these galaxies, so I need to look at all of the boxes. Okay. I've mentioned a few times that different simulations look at dense metal poor gas mass, and so why should we care specifically about the dense metal poor gas mass? It's because we want the situation on the right and we don't want the situation on the left. If you have a cloud of gas and it has a lot of metals, it'll cool more efficiently, and so it'll fragment and you might produce a bunch of stars, which for some people is a good thing, but for me that's not a good thing. I want one big black hole. So that's why we want dense gas so that it collapses gravitationally. And we want it to be metal poor so that it doesn't cool as efficiently and you don't get a bunch of fragmentation and a bunch of stars, which would also then blow gas out and you would get rid of more material that you could use to make a black hole. So these are the models that I am going to talk about for the rest of this talk. I'm, of course, going to run the fiducial Santa Cruz Semi-Analytic model. So this is the one, remember, where every single galaxy gets a black hole. But then I'm also going to have some models where I only consider a halo mass threshold. So if you remember, I said a lot of cosmological simulations just use a halo mass threshold. And that's what this last model at the end is trying to replicate. This would work out to a halo mass threshold of 10 to the 10. So everything heavier than that will get a black hole, and everything below it will not. The other halo mass thresholds, they're not a thing because of a physical reason, it's a computational reason. Again, if you remember that these different box sizes have different mass thresholds, I'm just trying to make sure I'm not putting a black hole into an unresolved halo that is like a bad data point. And then for all of these, I also take into account the dense middle pore gas mass. So I do some models where you don't need that much dense middle pore gas, and other models where you do need more. So just to relate the legend back to what I was saying, the different colors are these different halo mass thresholds, and the orange one is the one that's like our proxy for cosmological simulations. The dashed lines are ones where we care about the dense middle pore gas mass, and the dotted line is where we don't care about how much dense middle pore gas mass you have. And the black line is the fiducial SAM. You don't see it on this plot because this is the seeding rate as a function of redshift, because there's no seeding rate in the original model because everything just gets a black hole right at the beginning. So it'll come up in the other plots, but it's not on this one. What we can see is that these halo mass only models, so the dotted lines, have a lot more black holes being seeded because we don't care, again, about the dense middle pore gas mass. So you might not have that much gas mass, and you'll still throw a black hole in those models. But for these dashed lines here, there are less black holes being seeded, and the gap between these lines are all the galaxies that are massive, but they don't have metal pore dense gas. What I think is really interesting is that we're beginning to see a turnover in the seeding rate in these models where you do care about metal pore gas. And so this is something that could probably be directly observable with future gravitational wave observations. So in my work before this, studying LIGO black holes, I would relate those gravitational wave mergers to the star formation rate that could have produced them. And so in the future, this is something that's directly testable. And the reason that there is a turnover is that in the more local universe, you get too metal enriched to have enough dense metal pore gas to make black holes out of. This is the black hole mass function. So it's the number of black holes that you would expect at particular masses. And so you can see, as you might expect, there's more low mass black holes than there is high mass black holes. And the fiducial Santa Cruz SAM model, the black line is above everything because everything gets a black hole, and so all the other models will be below it. You can see differences between the models more at low masses. So these lines are kind of staggered, but then especially as you get up to the larger box size, which has the larger masses, you can see these lines all kind of converge and are on top of each other. And so this is indicating that with larger black holes, you won't be able to see seeding signatures as much as you could with lower mass black holes. And the reason that this is happening is that these black holes are massive because they're accreting mass, and as they're gaining more mass in addition to their original seed mass, it's erasing any signature of the original model that produced them. So this made me really interested in which regimes does the seeding mechanism and merger mechanisms dominate, and what regime does accretion dominate. So this is a plot of redshift and halo mass, and then the color is the fraction of black hole mass from seeding. And this is in the different box sizes. So that's the smaller box size, and this is the larger box size. And so what we see is from this black area, this is where there's no accretion happening. All of the black holes have the mass that they have because they were born that way, or they merged with another black hole that was also born the way that it was. And then these colors are where you actually have accretion happening. And so you can see in the smaller box sizes, we hardly get any accretion happening at all. And then we need the larger box sizes to get accretion. And so I kind of think of this as this is the gravitational wave regime, and this is the regime where maybe JWST can look at stuff. So this is the luminosity function, and I'm only showing it for graph 35, which is the biggest box size, because like I said, there's not accretion happening in the other boxes. And we can only tell the most stringent possible model apart from the others. So this like loosely dashed line has the highest halo mass threshold and the highest dense metal pore gas mass threshold. That's the only one that is different from the others. And so again, this is showing that at least at redshift 6, you can't tell different seeding models apart from your luminosity function. So some of my next steps is I do not like that I have all of these plots and all of these models, like graph 5, graph 15, graph 35, and then all these different halo mass thresholds. I want to make these a cleaner plot, and I want it all just on one plot. And so I'm currently exploring using extended merger trees that take these boxes and with machine learning extend their resolution up to the graph 5 resolution so I can combine everything nicely. And so when all of you read the eventual paper, you'll see that the plots are a lot more succinct. So that's what I'm actively working on right now. Of course, coming from a gravitational wave background, I want to investigate mergers and see what sort of signatures might be apparent in future observations, such as with LISA. And especially because I'm showing that you might need the low mass black holes to tell seeding models apart, I think we might really rely on gravitational waves, but maybe I'm really biased. And also I want to vary the seed masses. I want to see if we change the seed mass, which is a parameter I can change in the model, how does that impact things like the black hole mass function, and what degeneracies are there? If you observe a black hole of a certain mass, what kinds of black holes could it have come from? Maybe there's a lot of different seed masses that can produce the same black hole at the end. So I'll probably also end up looking at different accretion models and so on. So to summarize in my last 30 seconds, it's a really good time to be studying seeding because this has been a mystery for a long time of where these black holes came from, and there's a lot of different models, but now we're pushing further and further back in time where we can actually see the eras where these could have formed. We can seed in lower mass halos than a lot of other models can, so we can probe a new area of host galaxy parameter space. We predicted turnover in the seeding rate because, again, there's too much metal enrichment at low redshifts. And we also predict that high mass black holes don't really show signatures of their formation, especially when you compare them to the lower mass black holes. Thanks.
Questions for Aryanna? Lika?
No, I have two mics. Isn't there a X number of mergers that are required before you start accreting? So can't you say, oh, if it is, I don't know, above this mass anyways, in our simulation, it has to have gone through this many merger trees or something like that?
Yeah, so these would have had to have, like you mentioned, gone through a bunch of merger trees to get to this point, but those mergers wouldn't have started accretion, and if they did, they would have shut it off. Sorry, can you repeat what your actual question is?
Sorry, it was a little chaotic. I'm saying you said your main conclusion in the end was that you cannot really see the formation or the those highest mass things. You don't know how they formed. Mm-hmm. But I'm saying, given your simulation, don't you require that they have to have merged at least X times before they can form anything that shows accretion?
Right, yes, they would have had to merge a number of times before we see that. So at least like with the luminosity functions being all on top of each other, we think it's because accretion kind of like blurs everything. Whereas with these lower mass black holes, we don't think that we have accretion blurring things. It would only be a bunch of mergers, which we have to look into more, because for these black holes, when they merge in the SAM, that would start accretion, but they're already above a threshold mass because they're halos are so small that their feedback will shut off accretion. So I think with these ones, they just don't have the additional blurring that accretion provides for the more massive ones.
Right. Interesting.
Yeah.
Let's thank Aryanna again.